We have already studied the theoretical part of stability for fully submerged bodies and the stability of floating bodies. Now we will continue with the analysis of stability of floating bodies. For our particular study in this chapter, we don't have to study the analysis for the fully submerged bodies. We are only studying for floating bodies. On the right side of the slide, we can see a picture of a cubic block, and the cubic block is floating inside a liquid. So some part of the cubic block is above the surface and some part of it is below the surface because the body is floating. In order for us to do analysis, we need to understand few parameters involved in this picture. The first one is called the HO. HO is the height of object from the bottom of the body to the top part of the body. The second one is HD, which is the location or the height from the bottom part of the body to the surface of the liquid. So HD over here is height of displacement. The third one is HD divided by 2. So why do we need to divide by 2? Because this is the location of your center of buoyancy. So the location of your center of buoyancy is denoted as YCB, and it is just HD, the height of displacement, divided by 2. So this is where you have your center of buoyancy. And the last one is YCG, which is the location of your center of gravity, and this is supposed to be at the centroid of the body. So this is the intersection between the vertical line and the horizontal line, which is half of HO. So because of that, the equation is H object divided by 2. This particular equation can only exist when we don't have any load attached to the body. If you have load attached to the body, or secondly, we have an object with different dimensions from the top to the bottom, the center of gravity cannot be calculated using this equation over here. Next, we have to know where is the metacentric center, but we do know that metacentric is something that you can calculate through this analysis. So we assume the MC to be anywhere in the vertical line over here. So for my particular study or my particular analysis, I assume it will be on the top. But later on, this is the location that we are trying to search for, and the location is denoted as YMC. So this YMC will determine whether the body will be stable or not. In order to find out what is YMC, it is a combination or an addition of BM, which is the height from the center of buoyancy, to the location of your YMC, plus the YCB, which is the height of your center of buoyancy. So in order to find out what is your YMC just now, it is equal to YCB plus BM. Okay, so because this is a 3D study, we have length over here going to the back, and also we have the base of the body to be from left to right over here. So if in case we want to study what is the volume of object, the volume of object is equals to L times B times HO or H object. The volume of displacement is equal to L times B times the height of displacement. Okay, based on the picture that I've shown you just now, which is this picture over here, we can actually calculate for the analysis of stability of floating bodies with this equation here. So the equation that we have involve YCG, which is already been talked about before, which is HO divided by 2, your YCB, which is HD divided by 2, and your YMC equals to BM plus YCB. So what is BM? BM is parameter that needs to be calculated in order to be included in this equation. So BM is equal to the second moment of inertia in a y plane or YY plane, and the second moment of inertia is different for each different surface. For example, this is rectangle, this is triangle, and this is a circle. For a rectangular surface, the equation is LB cubed over 12. A triangular surface is LB cubed over 36. And for the circle surface or a round surface, it is pi r4 over 4. Okay, what is the meaning of the area of surface? Okay, the area of surface is the area of surface that is meeting the surface of the liquid. Okay, usually for the study for this chapter, the body is uniform, where the surface at the top will be the same as the surface at the bottom. So we can consider the surface meeting the surface of liquid to be AS over here, and for a rectangular shape like this, it is equal to L times B. Okay, so in case you want to understand more on this, area of surface for a rectangular is L times B. Area of surface of a triangle, doesn't matter whether the triangle is that shape or this shape, is equal to L times B divided by 2, and area of surface for a circle is equal to pi d square over 4. Or if you use pi r square, it will give you the same answer also. So over here, you already know the surface, 3 different surfaces that we are using, and for the volume of displacement, it is just the area of surface multiplied by the HD. Okay, so at the end, if you put in the numbers inside for BM and you add in your YCB, you will get the answer for YMC. If your YMC is higher than YCG, you will have a stable body. If your YMC is lower than YCG, you will have an unstable body. And if your YMC is equal to YCG, you will have a neutrally stable body. Okay. In order for us to understand the analysis, I have provided you an example, which is here, example 1, a body without any external load. And the question over here asks, a solid cylindrical rubber spoil buoy is floating in seawater as shown in the figure. So some part of this is on top of the surface and some of it is submerged in the body, in the liquid. And the specific gravity of the rubber spar buoy and seawater are 0.95 and 1.03 respectively. So the density of seawater is 1030 kilogram per meter cube. The density of the rubber is equal to 950 kilogram per meter cube. The diameter of the spar buoy is 0.5 meters, so the diameter here is 0.5. So if the diameter is 0.5 meter, the radius should be 0.5 divided by 2 equals to 0.25 meter. Okay, so determine the depth D of the spar buoy immersed in seawater. So D over here, it's actually, if you do calculation, we usually put it as HD. And the stability of spar buoy from the metacentric height. So you want to know whether it is stable, unstable, or neutrally stable. Now we will answer this question. So for example 1, the first question asks us what is HD. So HD can be searched through this equation. FB is equal to W. So rho fluid GAHD is equal to rho object GA height of the object. Because the rubber buoy is a cylinder, we don't have any load on top, and we can see the surface area to be uniform from top to bottom. So we can consider that the area for top and the bottom should be the same, which is the HD and HO should be the same, and gravitational acceleration should be the same also. So we end up with density of fluid times H, height of displacement, equal to density of object times the height of object. If we rearrange the equation, it is equal to rho object, H object divided by rho fluid. And if you put numbers in, 950 multiplied by 5 divided by 1030, so your HD should equal to 4.612 meter. Done for the first question. For the second question, we need to start by searching what is the YCG for this picture. YCG, center of gravity, is equal to H object divided by 2. Once again, this equation is here because we don't have any no load in the picture, and because it is a uniform body. So the surface area is the same, and we don't have any a different load distribution from top to bottom. Okay, so we can do this equation like this, and it is just 5 divided by 2 equals to 2.5 meter. Alright, your YCB is equal to your HD divided by 2 equals to 4.612 divided by 2 equals to 2.305 meter. Right, next we have to find out what is your BM. So the BM for this question is equal to second moment of inertia in a YY plane divided by volume of displacement. So we do one by one. For IYYC, it is equal to pi R4 over 4, because the surface area over here is a circle, so it is equal to pi multiplied by 0.25, this is the radius, divided by 4. So your IYYC should equal to pi so 3.068 times 10 to the power of negative 3 meter to power of 4. Okay, your volume of displacement should be equal to the area times HD, and the area is pi d square over 4, or if you want to use pi r square is good also. HD is just HD, the height of displacement. So this is pi 0.5 square over 4 multiplied by HD, which is 4.612. So your volume of displacement should be equal to 0.90 0.9056 meter cube. Okay, so we have IYYC, we have volume of displacement, so BM is equal to 3.068 3 divided by 0.9056. So your BM should be equal to 3.388 times 10 to the power of negative 3 meter. Okay, so we already find out what is the BM, so we can find your YMC. So YMC is just BM plus YCB. So BM is 3.388 times 10 to the power of negative 3 plus your YCB, which is 2.305. So your YMC equals to 2.308 meter. Alright, we are not done yet because the question asks us whether the body is stable or not. So we need to compare between your YMC and your YCG. So by comparing those, we see YMC is 2.308 while YCG is 2.5 meter. So YMC is lower than YCG, thus the body is unstable. So what will happen? The body will have a tendency to move to the left or to the right because it is unstable. Okay, we are done with example number 1. Okay. We will continue with example number 2. For this example, the body is attached to external load, so the calculation for stability will be a bit different from what we did in example 1. So a sand boat is used to transfer sand from a quarry to a factory along the river stream. So this is the sand boat. On the left side is the front view, and on the right side is the side view. So the mass of the sand loaded into the boat is 50 tons. Determine the stability condition of the sand boat by calculating YMC. Okay, so from here we will see that the mass of the sand loaded to it is 50 ton. So 1 ton is equal to 1000 kilogram. So 50 tons is equal to 50,000 kilogram. Okay, so the load or the mass of the sand is 50,000 kilogram. From here, the question has already given us what is the CG, and CG is 1.5 meter from the floor of the body, and the total height over here, HO, is equal to 2.4, and here this is YCG, and YCG is equal to 1.5. The base is 2 meter and the length from the side is 10 meter. And the density of freshwater river is 1000 kilogram per meter. Now we will try and answer example 2. To begin with the answer, we need to change the mass of the sand, which is 50,000 kg, to weight. And how we do that? By multiplying the mass times gravitational acceleration, which is equal to 50,000 times 9.81. So the answer for that will be, the weight is equal to 490,500 Newton. Okay, so the weight of the sand is 490,500 Newton. Now, from the weight, we can actually find what is HD by using this equation, FB equals to W. So, rho fluid, G, A, H displacement is equal to 490,500 Newton. So, we will bring this to the bottom here. So, it becomes HD equals to 490,500 divided by density of fluid, which is water, G, and also the area. The area for this is a rectangular area, which is length times base. So HD is equal to 490,500 divided by 1000, and the gravitational acceleration is 9.81, and the area is 10 times 2. Okay, so total HD should be equal to 2.5 meter. Okay, when we already get HD, so we list out the YCG. YCG from the question is 1.5 meter. The YCB is just your HD divided by 2, which is equal to 2.5 divided by 2. So YCB is equal to 1.25 meter. Okay, so to find out what is your YMC, the YMC is equal to YCB plus BM. And first, we need to calculate the BM. So BM is Iyc divided by volume of displacement. The Iyc is equal to LB cube over 12 because this is a rectangular shape. Okay, and the VD over here is equal to the area times HD, which is equal to L times B times HD. So we will try and solve it one by one. Iyc is equal to LB cube over 12 equals to 10 times 2 cube divided by 12. So this is equal to the answer for it is 6.667 meter to power 4. And then for V displacement, it is equal to L times B times HD. So it is equal to 10 times 2 times HD, which is 2.5 meter. So this is equal to 50 meter cube. And your calculation for BM will be Iyc, which is 6.667 meter to the power of 4 divided by 50 meter cube. So the BM for this question is 100, or we can do it this way, 0.1333 meter. Okay, this is for BM. So the YMC is equal to YCB 1.25 plus BM 0.1333. So this will be equal to 1.383 meter, and from here we need to compare to your YCG. So the YMC is 1.383 and the YCG is 1.25. So the YMC is lower than YCG, so this is an unstable condition. Okay, so this covers the calculation for example 2. By the end of example 2, we have covered the analysis on stability. So we have covered buoyancy in the past plus stability for today, and I hope you will understand and make use of all the knowledge that I have given to you. And we will see you again in the next chapter, which is on Bernoulli's equation. See you again. Bye.